Awesome. Let me share my screen. So hi everyone, thanks for joining today. Smaller group today, but super excited to welcome you to Multimodal Weekly. This is a weekly virtual webinar series hosted by the team at 12 Labs. And for those who know about us, we are in an early stage AI startup building multimodal foundation models for video understanding. We've been meeting weekly on a weekly basis since last year, more than a year and a half now. Some of the topics that we tend to cover include news research in multimodal AI and foundation models. We have developers building interesting application in different verticals come talk about their projects. Sometimes some startup founders come in talk about their respective companies building in the space, and we have partners and team members talk about how to use our platform and API. In some of the recent session, we have a strong focus on the research community. So I've been inviting a lot of folks working at the intersection like multimodal and video understanding, right? Ranging from say benchmarking for multimodal reasoning to video instruction tuning to different aspect of video reasoning to video summarization, etc., video captioning. So that's a little bit of context. It's a recent session. For today's session, we have two speakers. Su Kai, currently the PhD candidate at National University of Singapore, who will talk about his latest paper called Enhancing Video Super Resolution via Implicit Resampling-based Alignment. So it's really focused on video processing, which is a very important topic for us at 12 Labs. And his second speaker is Bohao Li, currently a PhD student at the Chinese University of Hong Kong. He will give a talk on his work called Seed Bench, which is a series of benchmarks actually for multimodal LLMs. And we're really excited to learn more about the development of this series and the implication on the community. And feel free to send your question on Zoom chat. I think we have a smaller group today, so you can just unmute and ask the question directly to speaker as well. So with that, I'll stop sharing my screen. And so do you want to just go ahead and go to your presentation?
Okay, can you share my screen now? Can you see my screen now?
Yes, I'm seeing it.
Yeah, thanks, James, for the nice introduction. So I am very happy to be here to introduce my work on CVPR titled Enhancing Video Super Resolution via Implicit Resampling-based Alignment. So image super resolution as an essential part of the modern computational photography is developed in the camera system of almost every phone we have nowadays. Following the same idea, video super resolution can also be used to improve our video capturing system. And it can also help us to restore old videos, improve the efficiency of the video compression, and even enhance the quality and frame rate of the video games. So when it comes to the understanding of the fundamental idea of the super resolution, I think it is very important to return to the very basic idea of the image itself. This will help us to understand what resolution actually is and what exactly being made super in super resolution. The formation of the digital photo is essentially a sampling process. Photons pass through the lens and reach to the sensor. For example, here CMOS, which then convert them into the digital signals. The light field in the real world is continuous in terms of the space-time. The CMOS array sample the light spatially, temporally, transforming what we see into discrete results. So what is resolution here? Resolution is defined originally as the density of CMOS sensor. And these signals then undergo a series of the transformation, including DAC, digital to analog conversion, demosaicing, denoising, white balancing, gamma correction, and compression, ultimately resulting in the image we receive. So if we describe this entire sampling process as the function G, the aim of the super resolution is to find the inverse of G, which we can then use this G to recover the image to any scale we want. Let's take a 2 times super resolution task as an example. We want to super resolve this image from the size of W times H to 2H times 2W. After expanding, we only know the value of these red pixels, and the value of the blue pixels are missing. And we need to guess it from what we already have. What method can we use? So the very easiest one is to use nearest neighbor interpolation. Basically, just copying the nearest neighbor into the current location. A more advanced version is that we can use a polynomial interpolation like bilinear interpolation, bicubic interpolation. These methods use more neighboring information and apply different level of smoothness of prior. Just for your information, the nearest neighbor requires low smoothness at all, and the bilinear interpolation requires L0 smoothness. Bicubic requires L1 smoothness prior. But as we see that determine the value of the red pixels and this whole process of sampling depends on the content of your image, maybe texture, maybe the objects in the image, and also the entire computational system of your camera. Simply relying on this smoothness as a tool is far from sufficient. So this is why we need to use data-driven approach to learn this inverse function of G. We apply the gradient descent to learn it from the data we have. So the problem of this image super resolution is essentially transforming into the training a neural reconstructor from the data. Here, I have some example for you, like SRCNN, EDSR, and SUMI-IR as an example for different backbones to do image super resolution. But what's the difference compared to video super resolution to the image super resolution? Let's come back to the diagram we have for the image super resolution here. So for video, we're required to upscale different frames simultaneously. So that means that we have this bunch of the groups of the frames together. We need to do upsampling of these groups together. And a very essential part compares to the image resolution is that we need to assemble different signals from different frames and combine the similar signal together to get a better reconstruction. And the way how we do the assembling is to propagate information between different frames. Like here, we have the propagation from the frame from t+1 to t, and also t-1 to t. We can also propagate inversely from t to t+1 and to t-1. So for each frame here, we have these concatenated features, not only from the current frame, but also from the previous frame and the future frames. The naive way to do this is by copy the information directly from the resource frame to the current frame. But if we look closer to the propagation, we'll see that the frames actually shift by the camera motion and upward motion, which means that the alignment by simply copying is not accurate at all, because there will be slightly shift at the spatial content. So spatial alignment is used here to improve the accuracy of the propagation, to make sure that we assemble the similar item signal together to get a better reconstruction. And we want to look closer to this alignment process. To better illustrate this spatial alignment, I want to make some notation changes here. So we then denote the frames so we're currently dealing with as the xt, which is the x at current time, and the frames where we propagated from at the reference frame, which is denoted by XX. And we approximate the motion between these two frames by the optic flow we have between these two frames. So the process of alignment can essentially be described as the optic warping between these two frames using the optic flow. Let's also look closer into this warping process. We'll see that the warping is essentially designed to define the process that compute the query location by offsetting the correct rate of its optic flow, which is x plus optic flow of x and y plus optic flow of y. So you may notice that the transformation coordinates of the green dots in the reference frame, they do not lie exactly in the grid of this discrete image because our optic flow is continuous. So in order to solve this, we need to rely on this neighboring pixel to do the resampling. Basically, this is the resampling function. We read it here, is that we need to do this continuous reasoning based on the discrete image we have here. And the process of the resampling can be divided as 4 steps. First steps, the image is first transformed into the continuous intensity surface, and the surface is then transformed. And afterwards, we sample the transformed surface into the new image, new discrete image. Here are some common used reconstructor, like sinc function, nearest interpolator, bilinear interpolator, bicubic interpolator. And we can see that this is the spatial filter shape of different interpolator and also the frequency response for them. We can see that they have different artifacts or different filtering on the low pass node side of your frequency, which means that it do not allow your pass the high frequency content from this frame, from reference frame to our target frame. Here's some small illustration of when we use these different types of the interpolator, how the image, reconstructed image looks like. So the nearest labeling, they provide this sharp results, but there will be some distortion because it will have the quantizing effect on your coordinates. The bilinear, bicubic, reversely, they can provide some smooth result, but it over smooths the signal, so we may lose some high frequency information. And here's the real world data. We can see that nearest label provides some very sharp result from the perception of our human eye, but there are some distortion of the straight line when your line is tilted to some angle. And compared to this, bilinear provide this smoother result, but it filtered out the high frequency content. Yeah. So when it comes to the resampling, there's a bottleneck in the high frequency propagation. So to solve this bottleneck of frequency in propagation, we should also use the neural reconstructor, just like the image super resolution. So this is the original resampling we have for the propagation. What we want to do here is that given the offset of the optic flow vector, delta x and delta y, we can divide it into 2 parts, the integral part and the decimal part. So integral part can be used to identify a window of reference points that will be used to aggregate at time t. So we can get the features from this window of the pixel. In addition, the positional encoding is derived from the grid index And we want to get the point feature also from the aligned frame, the frame we want to be aligned. And this is from the time t. And these two features denotes the semantic features of the points we want to aggregate it. And we then derive this sinusoidal position encoding from the decimal offsets. Because it's decimal offsets, it represents the subpixel perception of our optic flow. And encoding this into a sinusoidal position encoding actually lift this two-dimensional information to higher dimension. And this enhance our processing ability for this high frequency data. So given all this information, the semantic feature of the window pixel and the position encoding of the window pixel, the semantic feature of the pixel we need to align it to, and also the position encoding where we obtained from the subpixel results. We then feed it into the coordinate network, which is composed by the set of the MLP. And through this MLP, we can get the key vector and also value vector, and also the query vector from the points we want to align. And the affinity matrix is computed comparing the similarity between the query and the key. And then we aggregate the information from the value using the affinity matrix. So this is essentially a attention module. Doing this have two advantages. One is that we don't apply any explicit smoothness prior here, which means that we don't filter out the high frequency data information. And also there's no quantization effects on the coordinates because we already embedded the subpixel information into this position embedding. So we don't have this distortion like the nearest labeling interpolation. So for the lateral structure, we follow the existing networks, like where they apply this second order bidirectional propagation. We only change these alignment modules for the propagation, which also means that our model is like plug and play, can be used in any types of the backbone. So here's the result for the alignment module. We compare our method to the flow-guided deformable convolution and also flow-guided deformable attention and patch alignment. On the different level of the optic flow accuracy, we get the best result among all these alignment methods. And here's some qualitative result for the RES dataset and also V4 dataset. And I'll show the videos of the reconstruction. As you can see that most of the high frequency content comes from this regular patterns of the buildings. This is the initial input, and this is the prediction of this input data. As you can see that for this building grid, we recover these high frequency patterns better than all these three baselines. So in the original data, essentially the case is that we only have this high frequency information in some frames. For example, we maybe only have this information of the building at the end of this video sequence. So the efficiency, how you propagate this information from the end of video, from the start of the video across the videos, is important because you can then use this high frequency data across the video to get a better results. And here the comparison with the state-of-the-art results, we can at the RES and V4 dataset, we get better result than the previous method. And for the Vimo 4D because it has less accurate optic flow, which means that it provides less accurate subpixel information. Then our methods will not work better than the PSRT results. Yeah. So for takeaway, the first thing that the high frequency information is crucial for both image super resolution and video super resolution. And for video super resolution, existing research works overlooks the frequency bottleneck in frame information propagation. So we propose implicit resampling-based alignment method, which addresses the issue by employing MLP-based coordinate networks to facilitate high-frequency propagation. So thanks for your listening. Here's the code base, GitHub base of this paper. I'm happy to take any question.
Awesome. Yeah. Thanks, Kai. I also put the GitHub link of the project into the chat as well for attendees who want to dive deeper onto it. Yeah, is there any like immediate question for Kai related to his presentation? Overall, I think it's definitely very important, right, to improve resolution for video in general. I think a lot of work at 12 is also focused on this stuff, video processing, and try to figure out like how to process like video frame most efficiently. So I think techniques like this really improve the quality of the frame interpolation, right? And that will have a lot with like,
Yeah, I think also because the formation of the image, this definition of image is changing right now. Because before we only view a image as the matrix of the pixel points, but now we have the image as the format of the 3D videos, a Gaussian splatting or the large image itself. Then the whole process becomes a bit of tricky here that in the nerve-based rendering data, we don't have this discretization. So how to transforming this discretized image information to the continuous domain, I think is also a very big problem. It's how to connect these two directions fused together.
Yeah, I think that's more along the temporal alignment, right?
Yeah.
Like working with, because I think you mentioned on the slides or spatial alignment, but I think with video we also need to work with the temporal alignment because frames are moving continuously through time, so we have to be able to align different frames across the time series, right?
Yeah. So yeah, because of the Gaussian splatting and this nerve, they rely on this decomposition of your object motion and also camera motion. So most likely you don't get this accurate object flow and accurate camera motion instantly. So you need to do this optimization based on what you get from any image clue or photometric clues for that. So I think this is also a future direction to go, is that how we ensure this combination from different frames to be accurate, to give a better supervision or reconstruction on the Gaussian splatting-based rendering technique. Yeah.
Great. Maybe just one final question from my end is, I know you're working with the computer vision and machine learning group at NUS, right? This is spearheaded by Professor Angela Yao, right? Who's I think she's pretty famous in like video and video understanding research domain, and have a lot of interesting work, data set, and different contribution to the field. Maybe can you just give like a high level overview about what the lab
what the group is doing, right?
Doing, and what are some of the exciting research direction that your group is tackling related to video understanding?
I think the idea of the video understanding is shifting this year, is that we want to do this from 2D to 3D. So since happening in our group is that before we have a group of people working on the 2D video understanding, like action recognition and temporal action segmentation. And we also have the group of people doing the human body estimation, shape estimation, pose estimation, hand pose estimation, stuff like that. So since a bit of shifting right now to the 3D world, it's like we want to do this both for action recognition and the pose estimation from the word coordinate of view is that on the 3D world. So we then also have the group of people working on the Gaussian splatting and the nerve-based rendering right now, is that we want to get some 3D hint from the 2D video itself, and then this 2D reconstruction, 2D recognition task from the information we reconstructed in the 3D domain. Yeah. So I think that our group is divided into basically 3 branches. One is the post estimation, 2 is action recognition, the third maybe it's like a 3D reconstruction. I think we help each others on different topics. The final goal, I guess, is like to understand the video not only from the 2D world but also from the 3D scene understanding and combining this 3D reconstruction structure with the semantic meaning in the video itself. Yeah.
Awesome. Great. Yeah, thanks a lot, Kai, for walking over that.
Yeah, thank you.
Yeah, so I think we can go ahead and move on to the second presentation. Yeah, Kai, do you mind stop sharing your screen so that Bohao can go ahead and start it?
Okay. Can you see my screen? It may looks black.
It's black right now, but let's wait for a few minutes.
Okay.
Can you try? Yeah.
It's still black again.
It's a black screen with the word Bohao Li has started screen sharing. So maybe we have to wait for a few minutes because the last time it was working, right?
Okay. Let me try to quit and enter again.
Okay.
Maybe it's still black again.
Let's wait for a bit. Let's wait for a bit, and then.
Okay.
Yeah, it's still black. Is there a problem with your laptop? Oh,
I'm sorry. I'm sorry. Maybe Zoom had tell me that it has some error. and it can't be used right now.
Mm.
Mm. I'm sorry.
Yeah, no worries.
Still black again. I'm s-
Or you can email me your presentation and then I can
okay.
share it on my.
Okay.
It's a PowerPoint, right?
Yes, it's purple.
Okay. Yeah, you can just email me and then I can share mine to see if it works.
Um,
Yeah, let me know when you send it over.
uh, I have sent my PowerPoint to your email.
Okay. 1 second. Okay. All right, I think I got it. Yep, I got it. Let me open it real quick.
Mhm. Okay.
All right, I got it. Let me share my screen. And you can present and just let me know when you want to move to the next slide.
Thanks a lot.
Yep. All right, can you see me? Can you all see my screen?
Yes, I can see the screen.
Yep. No, go ahead. You can go ahead with your presentation.
Okay, and hello everyone. My name is Bohao Li, and I'm a PhD student in the Chinese University of Hong Kong. And in this time, I will present my work, the benchmarking multimodal large language models. And you can okay. In this presentation, I will present our method in two four parts: motivation, method, and experiment, and the conclusion to introduce our the bench work. And first of all, I will introduce the motivation. The motivation part contains the current multimodal large language models and the previous benchmark. ChatGPT and GPT-4 has attracted a lot of people's attention in this time. And at the same time, more and more people pay more attention onto multimodal large language models. For example, video chat and mini GPT-4. These models can deal with images or videos and answer corresponding questions. However, these models only demonstrate models' ability by showing some cases. Also, there is a lack of method to qualify this method abilities. Hence, there exists a need for a benchmark for comprehensive analyze models from different aspects. And indeed, there exists some benchmarks that can evaluate models from multimodal. Take the V2 as an example. It gives models an image and a corresponding question to answer. However, it needs models output the answer exactly. Takes and it needs the models to output open form, and it has limited evaluate aspect. Also, there are other benchmark like LVLM. However, this benchmark need to take GPT for open form evaluation, which GPT take to evaluation will bring bias into model evaluation because there are many models take the GPT to generate corresponding pre-trained data or fine-tuned data. Hence, it will bring bias for evaluation. And so after introduce our motivation, I will introduce our work, step 1 and step 2 to solve previous problem. And here is an overview for step 1. We evaluate multimodal large language models into 12 dimensions, and in these 12 dimensions, we use 9 dimensions to make up spatial understanding part of step 1. We also call it as the image part of step 1, and other 3 dimensions to evaluate models' temporal understanding ability. We also call it as the video part of step 1. And here is corresponding example for each spatial dimensions. And we use nine tasks to evaluate multimodal large language models in spatial understanding of image of input image information. And here is our pipeline to generate corresponding questions in spatial understanding of step 1. For that source, we use 63 million as the data source and use different models to extract different aspect information from an image. Then we use GPT-4 to integrate information and produce corresponding questions and answers. After that, we use human annotation to improve our benchmarks question and answers quality. And though there are many tasks in videos, there are many repeated tasks in spatial understanding. So we pay more attention on temporal understanding of video. Hence, we use these 3 dimensions to make up our temporal understanding of step 1. And here are corresponding cases. However, step 1 pay more attention on single format questions. In fact, question format could be more complex. So we merge some complex format questions such as interleaved image and test data to evaluate models. And for the models output, we evaluate models image generate. From the image, more complex format will have higher level and step to contain the most complex question format in current benchmark. Based on the step 1, step 2 contain 27 dimensions to evaluate models, which this dimension could be divided into 6 parts. Single image and text comprehension, multi-image comprehension, video comprehension, interleaved image and text comprehension, image generation, and image text generation. And here is corresponding demos in the part 1, which I taught in the previous page. Part 1 contains single image comprehension, multi-image comprehension, and video comprehension cases. In this part, we input a single image, multi-image, and videos as a home part, and then we input the questions to evaluate multimodal large language models. And here is interleaved image. And here is the corresponding cases for part 2 and part 3. Part 2 is interleaved image and text comprehension. Part 3 contains 2 parts: image generation and image text generation. This part, we hope to evaluate models' ability into more complex question format and image context generation. And here is corresponding data source for seedbench 2. For different dimensions, we use different data to make up corresponding questions and answers. And after that, I will introduce our experiment of seedbench 2 contain its strategy, result, and some observation based on the results. For the test output, we used PPL strategy to evaluate models to avoid the options A, B, C, D influence to the models. For example, we take the question in the image as an example. We first input the image and the corresponding questions into models. Then we compute each option's loss, and we compute each options content loss. Then we select the lowest lost options as the model's output. And for the image output, we use the clip similarity to evaluate models generate images semantically correct. For example, we take the model's output image as output image as A. Then we compute the output generated image to the options A, B, C, D images and compute it clip similarity. Then we select the higher similarities as the model's selection. And here is our evaluation result for 23 models on our seedbench 2 for different levels and different parts. And here is the detailed performance for these 23 models on single image comprehension. From the performance tables, we found out that all models are struggling with visual reasoning tasks, such as understanding chart and visual mathematics. And here are 23 models detailed performance on part 2, part 3, and multi-image and video part. From the tables, we can find out that models has difficulty in comprehensive with interleaved image and test data. And what's more, there is only a small numbers of models has the ability to generate image and the task based on the input text and the image. Also, these models in the box are trained on the video data. We call it as a video LLM. However, they don't show their abilities in temporal understanding. Also, these models in the box are trained on the interleaved image and text data. They also demonstrate their abilities in deal with similarity format questions. And last of all, I will introduce our conclusion, which including our contributions, communities, and extensions. As the seedbench contain a large numbers of high quality annotation, lots of multimodal language models evaluate on seedbench, such as Lavas, EMU, and Unified IO. and for easy comparison, we make an online leaderboard and update GPT-4v Gemini's Cloud 3 result for Seabench. Also, others could upload their models result on leaderboard online. For extension, we have introduced Seabench 2 Plus. It mainly focuses on evaluate models' ability in text-rich visual comprehension, and this bench contain 2 kilos question answer pair, and the questions is managed in 63 text-rich 63 text-rich screens. And here are some demos in this benchmark. For these questions, we managed divide into 3 parts: charts, maps, and webs. These questions all need to obtain text in the image and 2 answers. What's more, we have proposed Seabench Edge, which is a comprehensive integration version of Seabench. In these versions, we have 28 kilos QA pairs and 34 dimensions to evaluate multimodal large language models abilities. And in these versions, we pay more attention on the interleaved image and text streams. We have added more interleaved image text dimensions to evaluate models, such as visual story comprehension and some few-shot image understanding. For example, few-shot segmentation and few-shot object detection task to evaluate models' abilities. Corresponding demos is shown in the left part. And that's all. If you have some questions, you can email for me, and thank you for your listening.
Awesome. Yeah, thanks Bohao for walking through it. So I stop sharing my screen. So we have roughly 5 minutes left at the webinar. Yeah, I saw a clap from BB. Anyone have any question for Bohao related to this work? I think it's a very comprehensive projects that cover a lot of routes on the benchmarking world. Oh, I'll show you if you got a question. Yeah, you can just unmute.
Okay, cool. Hi, thanks so much for hosting, James. And thank you so much to our speakers. I was just wondering, like, in terms of your work, like, what are some like practical industry applications where your work has like ripple effects? Because I'm more in the like industry side, and I'm not too familiar with like the research, but it's all really interesting and really cool. Thank you so much. Yeah, that was super cool. Both of the talks were really cool.
Okay, thank you for your listening. Your name's the benchmarks application. Okay. I think I also see CMU has introduced their works in the previous and MMMU pay more attention on evaluate multimodal large language models in some knowledge comprehension. However, Seabench pay more attention on more tasks to find out which task models couldn't do better. And in our performance, we found out that current models may do not good at some reasoning. This is MMU's works, and we also found out that models may couldn't deal with some interleaved image and test data, which is more suitable in users. And I think benchmarks is the key to find out that most these models disadvantage and and some tasks they cannot deal with, and I think this is benchmarks and I think this is what our students to do. Okay, I'm so sorry. My English speaking is not. I'm not so
Okay,
good.
totally good. No, sorry, I'm just not very technical, so I have a hard time understanding like technical lingo. But yeah, you did a really good job. Thank you so much. Yeah,
Oh,
both you
okay.
and Kai did a really good job. Thank you. Sorry, I'm not very technical, so
No worries.
thank you for your patience. Yeah.
I think,
Okay.
yeah, I think what he's talking is like, I think the goal benchmark is to evaluate, multimodal models, right? In a holistic and fair manner. So having high quality benchmark will allows researchers to develop better models, and therefore, business startups, people can use those models in the industry and get better results. So the development of this benchmark in the academia will allows, like, say, these companies to like understand what works and what doesn't, that trick the products to meet user needs, right? I think that's I guess like the way I can explain it to like non-technical audience. Yeah.
Yeah, thank you so much for your patience. Thanks.
Yep. No worries. And Kai, do you want to also answer PV question? Like, what would be the implication of your work on video super resolution?
I think the lead for the super resolution in the large data area is like there's still a gap between the current super resolution field to the large language model community right now. My personal feeling is like we should add more semantic meaning handling in nowadays super resolution system. In that way, we can incorporate the like word embedding and also for this multimodal data set into the super resolution itself. Yeah.
Yeah, so I think what you mean is right now his research domain super resolution is can be improved a lot with the incorporation of new techniques from Gen AI, including like large language model, right? Like leveraging, let's say, OpenAI, GPT-4, or like Anthropic model to help improve the process of getting frame interpolation and extracting relevant insights from the video. I think that's
yeah, and I think the way how we use generative AI when combined with the super resolution and also the frame alignment, this gives this generative AI more grounding on the physical based or the frame-wise based this spatial and temporal reasoning into that generative AI itself. So we're not only generating some random video from one single image, but we're generating some high frequency, high super resolved data from the data we're given. Yeah.
Okay. Yeah.
Thank you.
Yeah. I hope that answers your question. Great. Awesome. Thanks, guys. So I think that we can conclude the webinar here. Thanks everyone for making it today. The recording of the session will be available on YouTube within, probably 4 or 5 weeks or so, and I'll be sure to include highlight that to the speakers so they can share it with their community. And once again, we host this webinar on a weekly basis every Friday. So if you find it interesting, subscribe to join our Discord community, and you can stay up to date with the next week's session. Yeah. Thanks everyone.
Thank you. Thank you, Jim. Thank you, everyone. Bye-bye.
Thank you.